So what do we need to know? Generally speaking, for a two-way table, whenever we are assuming independence, a cell's expected count represents the combination of a row variable category with a column variable category. So we have a row and then we have a column. And remember that we start talking about categorical variables. And it can be computed based on the cell's corresponding row proportion and also the cell's corresponding column proportion. And also, the next thing that we need to consider is the total number of observations in the table, which is called the grand total. These are the information that we need: corresponding row proportion, corresponding column proportion, and the grand total. Do we have a formula for that? Of course. As a formula, this is expressed as expected count equals to. We have to multiply three things: row proportion times column proportion times grand total. The expected count is equal to row proportion times column proportion times the grand total. Since the row and column proportions are equal to the total for each category divided by the grand total, we have the following. So our formula says, in mathematical form, expected count is equal to row total divided by grand total, which gives us the row proportion. So the formula for row proportion is row total divided by grand total. Column proportion formula is column total divided by grand total. And grand total, you just write it down. Note that since grand total is on the numerator, also on the denominator, you can cancel out the common factor. So what's left? A shorter version of this formula, which says, hey, the expected count is equal to row total times column total divided by grand total. So this is the formula that we're going to use when we are dealing with our table. Okay, let us go over a couple of examples until we feel comfortable about using this formula and finding expected count. We need expected count later when we are dealing with chi-squared. Let's get back to our table about science fiction film survey. Remember that the responses that we had, yes, no, and the knowledge level. Very knowledgeable, moderately knowledgeable, having little to no knowledge. We're going to follow the formula. What was the formula? Write it for us. Row total, so remember that. We had the expected count. Expected count equals to row total times column total divided by the grand total. We're going to find the expected count for each of these cells separately. So for the very first cell, let me find the very first page that we have. This is our very first page that we started talking about chi-squared and the expected count. So take a look at this. These were the original data that were collected for us. 120 to 80, the total was 400, and 75, 175, the total was 250, 105, 245, the total was 350, and the total for yes, 300, the total for no, 700, and the total number of people who participated in the survey was 1,000. Very well. So our formula says row total times column total divided by grand total. Row total, which is 400, column total, which is 300. We multiply these together and divide by the grand total. Row total times column total divided by grand total, which gives us 120. So let's highlight this number here. 120 is the expected count for the first cell. For the second cell, the row total is 400, the column total is 700, and we divide it by 1,000. We get 280. For the first cell on the second category, row total is 250, column total is 300, divided by the grand total, which is 75. For the second cell on the second category, the row total is 250 and the column total is 700, divided by the grand total, which is 1,000, it gives us 175. Let us move on to the last category. The row total is 350. The column total is 300. We multiply these together, divide by the grand total, which is 1,000. The number expected count that we have is 105. And the last cell that we have is related to the last category. The row total, 350. The column total, 700, divided by 1,000. The expected count for the last cell is 245. Very well. So how do we compute a chi-squared statistic? What did we do? We calculated expected count for each of these cells based on the information that were given to us. Now we're interested in calculating something new, computing a chi-square statistic. Remember that chi-square is tilted x to the power 2. This is chi or chi square statistic. Just as you did for a one-way table in previous lessons, you can compute a chi-square statistic for two-way tables. As you will see in the next lesson, the chi-square statistic will be useful in assessing the strength of evidence against the claim of independence. So that's the main use of chi-square. We can assess the strength of evidence against the claim of independence. Well, computing a chi-square statistic for a two-way table is very similar to developing the chi-square statistic for a one-way table. To compute a chi-square statistic for a two-way table, first, we need to calculate the expected counts. The expected counts. This is our very first step. The formula for expected count for each cell is row total times column total divided by grand total. Expected counts are computed for each combination of a row variable category with a column variable category based on the corresponding row totals and column totals. The exact same thing that we did for our table here. Note that totals in a table do not represent categories. In other words, any row or column total presented in a table is not considered a category of any of the variables. These are all counts. To compare observed counts with expected counts, carry out the computation for each combination of row and column variable categories. Well, we know that to compute the expected count for a combination of a row variable category with a column variable category, we follow the following formula. Expected count is equal to row total times column total divided by the grand total. Very well, give us an example. Let's take a look at this example together. Just as when you were computing chi-squared values for a one-way table, when calculating expected counts, it is fine if the expected counts are in fraction form, in decimal form, in general, if they are not integer, that's absolutely fine. You should generally not round expected counts to whole numbers. So note that if you do the division and you don't get an integer, that's fine. Do not round the expected counts. Also note that the sum of your expected counts for a given row should equal that row's total in your sample, and the sum of your expected counts for a given column should equal that column's total in your sample. Well, let's take a look at this example here. What do we have? The results of the sample one that we presented in previous lecture is given in the following table. Remember that we came up with numbers. These are not real numbers. We just came up with these. Responses, yes, no. The very first category related to knowledge level, very knowledgeable, moderately knowledgeable, and having little to no knowledge. Remember that we added the numbers the way that it add up to 400. So 300, 100. The total is 400. 250, 250, 100, 250, 350. The sum, the total of the very first column is 600. The sum, the total of the second column is 400, and the grand total is 1,000. This is our grand total. Okay. The next step is to calculate the expected counts. So this is where our computation starts. What are we going to do? We're going to follow expected count formula. Expected counts formula is the row total times column total divided by the grand total. So for the very first cell, the row total is 400. The column total is 600. So 400 times 600 divided by the grand total. 400 times 600. 400 times 600 divided by 1,000, which is 240. The expected count for the first cell is 250. The expected count for the second cell, row total, is 400. Column total is 400 divided by the grand total, which is 1,000. It gives us 160. For the next cell related to second category, knowledge level, moderately knowledgeable. So the row count is different. 250, the row count, the row total, divided by the column total, 600, divided by the grand total, 150. For the second category, second cell, row total is 250 times column total, which is 400, divided by grand total, which is 1,000. It gives us 100 as the expected counts. And the last category, first cell, total for the row or row total is 350. Column total is 600 divided by the grand total, which is 1,000. So it gives us 210. And finally, the expected count for the last cell, row total, 350. Column total, 400 divided by grand total, which is 1,000. So by doing the computation, we get 140. This is our very first step in computing the expected counts. We have 1, 2, 3, 4, 5, 6 cells, and we get 1, 2, 3, 4, 5, 6 expected counts. Our very first step is calculation of expected counts. Let us move on to the next step. So in very first step, we calculated the expected counts. Since the expected counts have been calculated for each variable combination, we can now carry out to the following steps to compute a chi-square value for a two-way table. So now we're going to calculate the chi-square. For each combination of row and column variable categories, we need to compute the difference between the actual count for the combination and the expected count for that combination. So in the next step, we need to calculate observed count minus expected count. We subtract expected count from observed count. Then in the next step, we're going to take each of these subtractions and raise them to the second power. After that, we're going to divide this number that we raised to the second power by the expected count itself. So first, we calculate the expected count. Then we do the subtraction. This is our step 2. Then in step 3, we raise them to the second power. In the last step, we need to divide that number that we raised to the second power by the expected count. And finally, in the final step, we're going to add all of these numbers that we calculated together. So this is the final step. Add them all. Okay. Let's take a look at our example here. What do we have? So observed count, expected count, observed count minus expected count, observed count minus expected count squared, and finally, observed count minus expected count to the second power divided by expected count. And the final step is to add them all together. So what did we have? We have the following table. This is the table that we worked with. Let's just put this right here. This was our table. Yes, and very knowledgeable. Yes, and very knowledgeable. The actual count is 300. No and very knowledgeable. No and very knowledgeable. The actual count is 100. Moderately knowledgeable and yes, 200. Moderately knowledgeable and no, 50. Having little to no knowledge and yes is 100. Having little to no knowledge and no is 250. These are all observed counts or the actual values that are given to us. These all go on the first row, actual values. These are our given values without any calculation. We don't need to calculate anything here, but in the rest of them, we all have the calculations, computations. So in the second row, we need to have the expected count. Expected count. It means that we followed our formula for expected count and we calculated these expected counts. Formula. This is the actual step that the calculation begins. So remember that for knowledgeable, very knowledgeable, and yes, we multiplied 400 and 600 divided by 1,000, the grand total, to get 240. As we calculated the rest of the expected values, we enter all of them here on the second row. expected counts. More computations. Well, now we need to take expected count, take observed count, and do the subtraction. 300 minus 240 is 60. 100 minus 160 is negative 60. That's absolutely fine to get a negative number. 200 minus 150 is 50. 50 minus 100 is negative 50. 100 minus 210 is negative 110. 250 minus 140 is 110. So we calculated the observed count minus expected count, and we have these numbers. The next step is to raise each of these numbers to the second power or multiply each number by itself. 60 times 60 is 3,600. Negative 60 times negative 60 is positive 3,600. 50 times 50 is 2,500. Negative 50 times negative 50 is positive 2,500. Negative 110 times itself is 1,200. 110 times 110 is 1,200. Well, more calculations. After finding the square of these numbers, we're going to divide those numbers by the expected count. Expected count on the second row. So we're going to divide 3,600 by 240. We are dividing 3,600 by 160. We are dividing 2,500 by 150 and so on. So we take each of these numbers and divide them by second row numbers, each one separately. And then we find our last row that we need. In the final step, the chi-square can be calculated. How do we calculate the chi-square? Statistic, the chi-square. Statistic is equal to 15 plus 22.5 plus 16.67 plus 25 plus 57.62 plus 86.43. The chi-squared statistic is 223.22. Remember that we don't need to round this number. Just leave it as it is. So we calculated the chi-square statistic for the first sample. Let's take a look at two more samples. Sample 2, and finally we're going to take a look at sample 3. So let's make this a little bit larger so everyone can see that. Change the focus a little bit. There we go. So for our second sample, we have the observed count given to us. We calculate the expected count as we did before. Then we compute observed count minus expected count. We calculate these numbers. And in the next step, we raise these numbers to the second power. And then the last step before calculating the chi-square, we divide the numbers that we calculated by raising the third row to the second power by the expected count. Then our chi-square is 2.32. 2.32 for sample 2. Remember that sample 1 chi-square was 223 for sample 1. The chi-square statistic is 223.22. This is sample 1. For sample 2, the chi-squared is 2.32, a number which is much smaller than 223.22. Let us take a look at the last sample, sample 3. Let's take a look at its chi-square. We have the observed count. We calculate the expected count. Expected count subtracted from observed count. And the number expected count, which was subtracted from observed count, raised to the second power. And we divide that by expected count to find the final numbers. It helps us to calculate the chi-square. So the chi-square statistic for the last sample, sample 3, is, well, as you can see, 359.62. Between these 3 chi-squared values, which one shows the strong relation, represent the strong evidence? When it comes to chi-square, we're interested in larger numbers. So between sample 1, sample 2, sample 3, the vote goes to sample 1 and also sample 3. But we're not happy about a small number like 2.32. It doesn't show a good association or good strength. So as we saw in previous lectures, by observing the data, we voted for sample 1 and also sample 3, and we said that, hey, sample 2 is not a good representative. Now we did the calculation, we came up with the exact numbers, exact values for our chi-squared. So the vote goes for sample 1 and sample 3. Extremely high value for sample 2, for sample 1 and sample 3, they take the priority. So these two shows very strong evidence. Sample 1, and sample 3 both give very strong evidence against a claim that variables are independent. Evidence against a claim that the variables are independent.